Okay, so what do we want to do? We have some binary data. You have some data with outputs zeros or ones based on some inputs. And maybe you can convert it into some probability distribution like this, or okay, between 0 and 1. And what we want to do is to fit a curve, a sigmoidal curve, to data that looks like this, or can be transformed into data that looks like this. So I've drawn the sigmoidal curve, and then I've drawn this raw data, which is binary. First, we will consider approximating purely binary data, and then we will. It turns out that the same method will apply when the data is not binary, but is more like this probability between 0 and 1. Okay. So we want to fit a sigmoidal curve that looks like this, and it's useful to consider a simple expression that approximates or captures a sigmoidal looking curve like this. Okay, and this is maybe the most common function that is used when you want to approximate a sigmoid. It turns out that any number of functions that have a functional form that looks like this, but this is the one that's most commonly used in this particular case because of some underlying probabilistic rationale. Nevertheless, for now, let's just go with this functional form. Okay, whenever you're given a functional form like this, you want to plug in some limits and see what values this function takes at various limits. Okay, let's plug in minus infinity for z. When you plug in minus infinity for z, you get e power minus of minus infinity, which is e power plus infinity. E power plus infinity is infinity, so you have 1 over 1 plus infinity, which is 1 over infinity, which is 0. Okay, so when you plug in z equals minus infinity, you get 0. Similarly, when you plug in z equals plus infinity, you get e power minus infinity, which is 0, 1 over 1 plus 0, which is 1. Okay, you get 1 here. Then when you plug in z equals 0, you get 1 plus e power 0. E power 0 is 1, so 1 over 2, which is 0.5. Okay, so you have these three limits, and then you can also show that because e power any real number, e power any real number is a quantity between plus infinity and minus infinity. Actually, sorry, e power any real number is at least 0. It's greater than or equal to 0. 1 over this quantity is necessarily between 0 and 1, and then it reaches the values of 0 and 1 at these limits. Okay, so sort of putting all this together, you can show that the curve looks like this. It starts out at 0, essentially at minus infinity, and then slowly rises up, and it has the value 0.5 when z equals 0, and then keeps rising until it asymptotes to a constant value of 1 as z goes to infinity. Okay, you can also show that this function is always increasing. You can differentiate this function once and show that it's a positive quantity. In fact, this is the slope of this function, and the slope expression for the slope of the function is e power minus z divided by 1 plus e power minus z whole square. This is a positive number, this is a positive number, so this is always a positive number, so it's monotonically increasing, and it so happens that the slope at z equals 0 is 1 over 4. Okay, but the slope everywhere is positive, right? The slope is close to 0 here, close to 0 here, but certainly everywhere it's positive. It reaches 0 at plus infinity and minus infinity, or limits to 0 at those limits. Okay, so that's what this prototypical sigmoid curve looks like. Now, clearly this curve, although it looks like some curve like this or some curve like this, it's not quite like that, right? Now, in what ways is it not quite like this? Or, of course, here this is piecewise linear, but let's say we want to approximate this piecewise linear curve with a sigmoid like this. What would we want to do with this sigmoid or this sigmoid to make it closer to this function? Okay. Now, this function, of course, has no freedom, right? So once you write this function, this is the curve. You don't have any ways of, well, fitting anything else, right? You're just stuck with this shape of a function there because there are no free parameters here, right? So what would we want to do to this function to be able to fit some data that looks like this, or this looks like this dotted data? Okay. So what would we want to do? We wanted to basically shift the sigmoid right or left. Right now, this function, for this function, the sigmoid basically has a threshold of 0. In other words, it goes from 0 to 1 around z equal to 0. So that's something we want to change. We want to be able to move the sigmoid right or left like so. And then we may want to basically increase the slope. We may want to approximate this function where the transition is steep, or we may want to approximate a function like this or data that looks like this where the transition is more shallow. Okay, so we would like to be able to shift the sigmoid, and then we would like to be able to change the slope of the sigmoid. And it turns out that if instead of z you actually replace z with this linear function of sigma, where you say z is actually b naught plus b1 sigma, and the whole function that you're trying to approximate to this data is actually 1 over 1 plus e power minus, within brackets, b naught plus b1 sigma. Now we have two free parameters, b naught and b1, and it turns out by appropriately changing b naught and b1, you can change the slope of the sigmoid and also move the center of the sigmoid, like where it rises from 0 to 1, or where it basically takes the value 0.5. Okay. So how do we change the center and the slope? We can quickly look at it. Of course, the center of the sigmoid, namely where it's located along the horizontal axis, that's when the output of this function equals 0.5, right? So it's halfway between 0 and 1. That's what we want to call the center of the sigmoid, right? Like this point is when the failure rate is about half, when g equals a half or something. So if we equate h to a half, what is that value of sigma? So if you can just set h equals 0.5, basically z equals 0, where z is this whole thing. You've set this whole thing equal to 0, b naught plus b1 sigma equal to 0, so that you get e power 0 here and 1 over 2, right, which is a half. So b naught plus b1 sigma equals 0, or sigma equals minus b naught by b1. Okay. So essentially the ratio of these two coefficients with a negative sign is where the center of the sigmoid is. So both these coefficients affect the sort of transition threshold, if you will. And then for this expression, you can look at what the slope is with respect to sigma. If you differentiate this expression with respect to z, you just get 1 over 4 because there are no free parameters here. Of course, if you differentiate this expression with respect to sigma to find the slope of this function h versus sigma instead of h versus z, then it turns out that this expression looks like expression for the slope at z equal to 0 is b1 over 4. Okay, so this slope of the straight line, or at least this linear expression, the slope of this linear expression, it turns out affects the slope of the sigmoid at the center line. Okay. So just by changing b naught, you can make b1, you can make the sigmoid very steep or very shallow. You make it very steep by making b1 closer and closer to infinity, and then you make it very shallow by making b1 closer to 0. You can actually make b1 negative, which can give rise to curves that look like this, a sigma that goes the other way, goes from 1 to 0, so that the slope is negative. And basically by changing b naught and b1, you can have something gradual centered around sigma equals 0, something gradual centered about sigma equals negative or positive, something steeper, something with a negative slope. So you can have any of these sigmas that go from 0 to 1 or 1 to 0s with centered anywhere and then with arbitrary slopes. Okay, so that's what this simple expression gives you. Okay, so let me stop there, and then we will pick up on how to approximate, how to fit this function now to data that looks like this in the next video.